Hello and welcome to another Algebra 2 and Trigonometry lesson. My name is Mr. Weiler, and today we're going to be working with some sinusoidal modeling. In other words, we're going to try to take some real-world scenarios that can be really well modeled with both the sine function and the cosine function, as long as we understand all those little pieces like the amplitude, the midline, the frequency, and the period. So what we're going to do is we're going to start by reviewing those pieces. Let's do it. All right. So when we take a look at trig curves that look like this or this, and of course whether we use sine or cosine is going to depend on the situation. But let me just sketch kind of a generic graph. Of course this could be a sine graph or a cosine graph, depending. But at the end of the day, we want to understand what the A, the B, and the C all are, right? So let's first talk, strangely enough, about the C value, right? The C value, that one, is my midline, right? It's that horizontal line that the trig curve rises above and falls below. The A, or more appropriately, its absolute value, is what's called the amplitude. It's how high above the midline and how far below the midline the trig curve the trig curve travels. And finally, B and P. B is what's known as the frequency, make sure to know this terminology, and P is the period. Remember, the frequency doesn't show up on the graph, but the period does. So the period is a horizontal measurement, right? It's the minimum amount of space or the minimum horizontal distance it takes before the curve starts to repeat itself. The frequency, what shows up actually in the equation, is related to the period by this famous formula. B times P is always equal to 2 pi. So when we're translating from a formula to a graph, we use that relationship to come up with the period. When we're translating from a graph back to an equation, we use the period to come up with the frequency. And we're going to get into each one of these in turn as we work through some modeling problems. So let's do that now. All right, the first problem. The tides in a particular bay can be modeled with an equation of the form D equals A times cosine BT plus C, where T, and this is important, where T represents the number of hours since the high tide, and D represents the depth of water in the bay. The maximum depth of water, that's important, is 36 feet, and the minimum depth is 22 feet. High tide is hit every 12 hours. So we're going to hit that maximum depth every 12 hours. Letter A says, on the axes, sketch a graph of this scenario for 2 full periods. Label the points on this curve that represent high and low tide. Well, let's do it. Now, one thing that's important is T represents the number of hours since high tide. So at T equals 0, we're at high tide, which means the water is as deep as it's ever going to be. Now, the fact that it hits its high tide every 12 hours means that after 12 hours, it will be hitting its high tide again. Just due to the symmetry, that means that after 6 hours, it'll be hitting its low tide, which is 22. Maybe I shouldn't put a dot there. In fact, maybe what would be helpful is almost some dashed lines, right? At the high tide and the low tide, right there. Of course, we can also say that after 18 hours, we would be hitting low tide again. And after 24 hours, we'd be back up to high tide. So it's going to look something like this. All right, there's our graph. Now letter B says determine the values of A, B, and C in the model. Verify your answers and sketch are correct using your calculator. That part we won't do, unfortunately, because I still don't have my electronic calculator working on this computer, but hopefully I'll get it eventually. Now you can do these in almost any order you want, and it's really quite up to you. I almost always personally come up with the value C first. Let me do that in a different color. You see, for me, the midline value, that is always the easiest because C is always the minimum y value plus the maximum y value divided by 2. In this case, that's going to be 22 plus 36 divided by 2. That's 58 divided by 2, and if I've done all my math correct, that means C is 29, and it is. Now, I typically do the amplitude next, or at least I figure out the value of A, so I'm gonna come up with this. Now, there's lots of different ways to figure out what A is. You could just take the maximum minus the midline, or the midline minus the minimum. The way that I typically do it is I do y max minus y min divided by 2. Remember what that does for you is it will give you this entire vertical distance if you do the max minus the min, but the amplitude or the A value will only be half of that. So 36 minus 22 divided by 2, that gives me 14 divided by 2, and that gives me A is 7. All right. Now finally, we have to figure out B. Now what's tricky about this is that a lot of students will immediately say, hey, the period is 12, so B is 12. But keep in mind that what we really know is we know the period. The period is 12, right? I'm going to do this down here if you don't mind. And we know that the frequency times the period is 2 pi. So we'll just put 12 in for the period and we'll solve for the frequency. So it looks like the frequency will be 2 pi divided by 12. You could leave it like that if you wanted to. Or a lot of people will prefer to make it into pi over 6. So our final equation is y equals 7 times the cosine of pi divided by 6 times t plus, where's my c? 29. There it is. Now, if we put this into our calculator, and of course we used an x there instead of a t, and we got the proper window, it would look like this. So I would encourage you right now to pause the video and do that. You're going to need the sketch in part C, okay? All right, well hopefully you did that and it's on your calculator. If it didn't work, you may want to check to make sure you're in radian mode. Of course, that can make a huge difference. You have to be in radian mode. Besides that, just make sure you have a window that goes from 0 to 24 in the x direction and at least 0 to 36 in the y direction, maybe even overshoot a little bit, 0 to 40 maybe. Anyway, let's take a look at letter C. It says tanker boats cannot be in the bay when the depth of water is less or equal to 25 feet. Really should say less than, but whatever. Set up an inequality. So I have to set up an inequality. I got to write one down. Set up an inequality and solve it graphically to determine all points in time on this interval when tankers cannot be in the bay. Round all times to the nearest tenth of an hour. Well, I'm going to have a problem whenever this depth, right, and this is the depth, whenever this is less than or equal to 25. So this is my inequality, right? When they say set up an inequality, that's what they mean. Now, how do I solve this? Well, what I do is I go into my calculator, and in y2, I put in 25. And of course, what that's going to do is it's going to graph a horizontal line 25 units above the x-axis. Then I'm going to use my intersect button to find a bunch of different intersections. That, and that. Those intersections, by the way, are at 4.2, 7.8. These are intersections along the x-axis. I know where they are on the y-axis. They're at 25. I'm not even writing that down. This is at 16.2, and this one is at 19.8. What's really cool is you can really tell that here is the portion where those tankers would get into trouble, right? Because that's where we're at a depth below the 25. So we can now say that any time in this interval, 4.2 is less than or equal to t is less than or equal to 7.8, or any time between 16.2 less than or equal to t less than or equal to 19.8, this would be our answer. Oh boy, there's so much filling up the screen. I'm sure my head is really tiny right now. Let me pause for a moment so you can take a look at that. This may be a problem you've already tackled in class, or it may not be. Either way, take a look. All right, I'm going to clear out the text and we're going to move on and do another modeling problem. Okay, I love yo-yos. Here we go. The height of a yo-yo above the ground can be modeled using the equation h equals 1.75 cosine pi t plus 2.25, where h represents the height of the yo-yo in feet above the ground, and t represents the time in seconds since the yo-yo was first dropped from its maximum height. So here's my height, here's my time in seconds. Letter A. Determine the maximum and minimum heights that the yo-yo reaches above the ground. Show the calculations that lead to your answers. Well, I think that many of you probably already have the knowledge to do this. So pause the video right now and take a shot at it. All right, let's go through it. Well, here's the cool thing. Let me write down the equation again. 1.75 times the cosine of pi t. Sorry about that s not quite being what it should be. Well, as we all know, that is now the midline, right? So that's that horizontal line. And this is the amplitude. So the maximum height is going to happen when we take that midline value and we add the amplitude to it. And that's going to give me, well, 4 feet. And the minimum height of the yo-yo is going to occur when I take that midline and I subtract the amplitude, right? The amplitude is how far above and below, above and below. And that's 0.5 feet. Letter B. How much time does it take for the yo-yo to return to the maximum height for the first time? So again, you got this person, doing the yo-yo. I can't believe I'm trying to draw this. Right, the yo-yo starts here, it goes down, and then it comes back up, right? We of course know that that's at 4 feet, that's at 0.5 feet, coming pretty close to the ground. The question is, how long? Pause the video now and think about this question. All right, did you figure out? The question is asking for the period. This thing is asking for the period, right? Now, the period is not pi. That's the frequency, right? So here's a situation where we've got the frequency, we need the period. Now, we know that the frequency times the period is 2 pi. So that means pi times the period must be 2 pi. But then that means the period must be equal to 2. So it takes 2 seconds for the yo-yo to go down and come back up. 1001, 1002, 1001, 1002. Convenient. All right, well, we're going to do another one in a second, so pause the video now and think about this problem. Think about how wonderful my picture is. All right, I'm going to clear out the text. Let's keep going. Exercise 3. A Ferris wheel is constructed such that a person gets on the wheel at its lowest point, 5 feet above the ground, and reaches its highest point at 130 feet above the ground. The amount of time it takes to complete one full rotation is equal to 8 minutes. A person's vertical position, 8 minutes. Oh, that's weird. I don't understand that. Who knows? Let's just cross that out. A person's vertical position, y, can be modeled as a function of time in minutes since they boarded t by the equation y equals a cosine bt plus c. Sketch a graph of the person's vertical position for one cycle, then determine the values of a, b, and c. Show the work needed to arrive at your answer. Well, notice it says a Ferris wheel is constructed such that a person gets on at its lowest point, which is 5 feet above the ground. So at t equals 0, they get on at 5 feet above the ground. And one full rotation takes 8 minutes. So after 8 minutes, they must be at 5 feet above the ground. Now, where are they at 4 minutes, right? That's a question. Where are they hitting? Well, what do we know? The highest point is 130 feet above the ground. So that must be right here. So the entire cycle must look like this. Now I'm gonna draw in another cycle. I know it said only one, but it's kind of nice, right? That would be at 16. That would be at 12. All right. Well, why don't you play around with the values of A, B, and C, and then unpause the video when it's time to see what each value is. All right. Well, many of these are straightforward, including my favorite, C. That's the phone. All right. Well, that was a phone call. Now we're back. So as I said, the first thing I'm going to go after, as you all know, I'm going after the value of C, right? Because all I have to do is I just need to take the minimum y value, the maximum y value. I just need to add those together, divide by 2. Yeah, okay, it's not the nicest thing. It's 67.5, but it gets the job done, right? And that's this. Now, strangely enough, I'm going to actually figure out the value of B next, okay? A is actually a little bit tricky here, and we'll talk about that in a minute. So if I figure out B, that's pretty easy. What I can figure out is that the period of this is 8. And therefore, 8 times the frequency must be 2 pi, right? That's that B times P equals 2 pi business, which means the frequency must be 2 pi divided by 8, which you could leave that way, or you could write it as pi divided by 4. So I have those two. Now for A. A is tricky, because it would be very easy to say, oh, all right, I'll take my maximum minus my minimum and divide by 2. And that would give me 125 divided by 2, which is also not the nicest thing on earth. That would be 62.5. The problem is, if you graph this curve, and I'm going to eventually graph it by hand in red, and we'll take a look at it. If you graphed this curve on your calculator, this is what you'd see. Oh, that did not work exactly the way I wanted. But you'd see something like that. It would have the right midline. It would have the right amplitude. It would have the right period, but it wouldn't be correct. It would have the person bordering at the maximum height, which granted could be kind of cool on a Ferris wheel. Not really. But it wouldn't be correct. So to make it correct, this has got to be negative. You see, cosine normally starts at its maximum, right? Just your garden variety cosine curve looks like this. If we want a cosine curve to start at its minimum, then we have to make the value of A be negative, all right? And that can be quite tricky. By the way, did you notice that none of these were modeled with the sine function? The sine function starts at its midline, and all of these either have been starting at their maximums or at their minimums, and that's better modeled by a cosine function. So, pause for a minute, write down anything you need to. Make sure that A is negative 62.5. All right, I'm going to clear out the text. Again, sorry about the interruption there. Here we go. All right, last little problem, multiple choice, then we'll stop the video. It says the possible hours of daylight in a given day is a function of the day of the year. All right, this kind of makes sense. In other words, like, in January, right, early in the year, there's very little light during the day. By the time you're in the middle of summer, June, July, there's a lot of light. And then as you head into the fall, of course, the light is going down again. It says in Poughkeepsie, New York, the minimum hours of daylight occurring on the winter solstice is 9 hours. And the maximum hour of daylight occurring on the summer solstice is 15 hours. If the hours of daylight can be modeled using a sinusoidal equation, what is the equation's amplitude? Go for it. It's a pretty easy multiple choice question. Well, the amplitude, which is the absolute value of A, will always be the maximum y minus the minimum y, all divided by 2. Well, here the maximum number of hours is 15. The minimum number of hours is 9 divided by 2. So that's 6 divided by 2, or 3. All right. So that's it. A lot of sinusoidal modeling gets to reading, so you got to be willing to read, It's about pulling out the maximum, the minimum, often the period, right? Pulling all of that out to be able to figure out the values of the amplitude, the midline, the frequency, and the period. Okay, I'm going to clear this out, and then let's finish up. So thank you for joining me today for a little sinusoidal modeling, right? Again, real-world problems that involve amplitude, midline, frequency, period, and the sine and the cosine functions. Hopefully this also made the sine and the cosine functions a little bit more, I don't know, relatable, perhaps? They really are useful in a lot of practical settings. For now, though, I'd like to say goodbye, and I'll see you next time. My name is Mr. Weiler. Keep thinking, and keep solving problems.